Okay, let's begin. So we were talking about canonical transformations. We defined canonical transformations by this condition. Okay. Pi Qi dot minus K plus dF by dt is equal to Pi Qi dot minus H. Okay. This is the definition we had. Am I right? Yeah, I think that's right. Okay. All right. Okay. And we said that f can be used as a generating function. We showed that f can be used as the generating function. Okay. How do we do this? We do this by choosing it as functions of or function of old, a mixed function, right? What we mean is a mixed function of old and new coordinates. Right? By coordinates, we also mean momentum. And new coordinates. Okay. So since it's coordinates, since it is momentum and coordinates, we'll call it as phase space coordinates. All right. Phase space coordinates. Okay, what do we mean by phase space coordinates? They are Qi and Pi. Okay, I hope that's not confusing. They are Qi and Pi. Okay, now how do we do this? There are four ways to this. Actually, there are a large number of ways to do this, but there are four basic ways of doing this. We said, okay, so let's talk about the function. It could be a function of first we'll write the old one and then the new. Okay, so we need to choose them in such a way that we have got half old and half new. Okay, that's what we said. Now, first we write the old one, the functional dependence. All right, so we have got old Q. We combine it with the new Q. That's one possibility, and this is called F1. Okay. Now, old you can choose as the old Q, and the new you can choose as the new momenta. Okay. In this case, you have got F2 of. So basically, you are taking each of the old one and combining it all the new things, right? In this way, there are four combinations in total. So you have F2 of Q, P, T. Now, notice that inside this thing, we are writing the functional order. All right. It's easy to remember if you write it like this. The functional dependence, the order of the dependence, we always write, first we write the old one and then the new. Okay, first you write the old one and then the new one. Okay, now you can take small p and combine it with capital Q. You can take small p and combine it with capital P. These are the four possibilities. All right, this we call F3 of P, Q, T. Okay. And here we have got F4 of P, P, T. Okay. This much is clear, isn't it? I think that's how we defined it. Q, 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 P, P, Q, and P, P. All right. These are the four things. Now, how do we find the transformation equations? Or how do we find the equations relating the coordinates from the generator? Okay. It's easy. If you want to find Q, okay, it's always dou F by dou P. Okay, Q is always related to P. The sign will fix now. Okay, if you want to find P, it's always dou F by dou Q. No doubt in that. If you want to find capital Q, it's always, okay, let's say it's proportional up to a minus sign. Okay, up to a minus sign. Q is always dou F by dou capital P, and capital P is always dou F by dou Q. All right. These are these are the relations. These are conjugate. Okay. If you have capital P here, you need to take derivative with capital Q. If you need small p, you need to take derivative with small q, etc. Okay. All right. So these are up to a minus sign. Okay. Up to a minus sign. Okay, I'm just giving you an idea to remember this. All right, up to a minus sign. Now, how do we fix the sign? How do we fix the sign? So, in order to fix the sign, you take each of this thing. All right. So, if you take F1, let's take first case. This much we know now. We take F1 of Q, capital Q, and T. Okay. Now, how do you find small p? Small p is dou F1 by dou Q. Okay. And we need also capital P. This is equal to dou F1 by dou Q. All right. Again, up to a minus sign. Now we fix the minus sign. Now we fix the minus sign. All right. So you remember the order inside this argument. All right. You remember the order inside this argument. You call this as first position, second position. Okay. Now you remember that the first position needs to be the coordinate. If the first position is coordinate and second position is momentum, then we have all plus. Okay. If one corresponds to coordinate and 2 corresponds to momentum, then we have all positive. Otherwise, we have negative. This is the easiest way to remember. All right. Now, if you look here you have got first position Q. No problem. The position is correct, so it's plus. Okay. Here you have got capital Q in the second position. All right. Capital Q is in the second position, but you should have capital Q in the first position, right? So we have basically changed the position. There's a minus sign. Is this fine? Is this what you asked, Rafiq?
അതെ ഫസ്റ്റ് പൊസിഷൻ അത് പൊസിഷനെ റെപ്രസെന്റ് ചെയ്യുന്നു, രണ്ടാമത്തത് മൊമെന്റത്തെ റെപ്രസെന്റ് ചെയ്യുന്നു. അങ്ങനെ ആകുമ്പോഴല്ലേ പോസിറ്റീവ് വരിക?
മൊമെന്റത്തെ റെപ്രസെന്റ്, അതെ, ഈ പൊസിഷൻ മൊമെന്റത്തുള്ള. പക്ഷെ ഞാൻ പറഞ്ഞു തരുന്നു, വാട്ട് ഐ എം സേയിങ് ഇസ് this is a way to remember, right? It doesn't matter even if you write it the opposite way. Okay, so this is how we write it. First we write the first old coordinates, and in the second we write the new coordinates. All right, by coordinates okay. I mean position and momentum. Okay, in the first position q ആണെങ്കിൽ ഇവിടെ നമ്മൾ dou f by dou q എടുക്കുന്നുണ്ടല്ലോ. So here we are taking dou f by dou p. Am I right? Okay. Now, if this okay. p comes in the second position, then this is a plus. If this p comes in the first position, this is a negative. Okay. So if q okay. comes in the first position, then this is positive. If this q is coming in the negative position, sorry, second position, it has to be negative. Okay. അതായത് നമ്മൾ dou f by dou q എടുക്കുകയാണ്. ഈ q ഫസ്റ്റ് പൊസിഷനിലാണെങ്കിൽ ഇവിടെ പ്ലസ് ആണ്.
ഓക്കെ ഓക്കെ.
അതുപോലെ പി ഫസ്റ്റ് പൊസിഷനിലാണ് നെഗറ്റീവ് ആണ്, ക്യൂ സെക്കൻഡ് പൊസിഷനിലാണെങ്കിലും നെഗറ്റീവ് ആണ്. ഇവിടെ നോക്കുകയാണെങ്കിൽ ക്യൂ സെക്കൻഡ് പൊസിഷൻ, അപ്പൊ ഇവിടെ മൈനസ് ഇട്ടു. ഇത് ഓർമ്മിക്കാൻ ഒരു എളുപ്പ വഴിയാണ്. പെട്ടെന്ന് ഒരു ക്വസ്റ്റ്യൻ കാണുകയാണെങ്കിൽ you don't have to find all these transformation equations. You can just give the transformation equations. Okay, you can be asked, they may give some
capital Q ഫസ്റ്റ് വരികയായിരുന്നെങ്കിൽ അത് പോസിറ്റീവ് ആയിരുന്നു ഇക്വേഷന്.
എക്സാക്ട്ലി.
ഓക്കെ ഓക്കെ.
അങ്ങനെയുള്ള കോമ്പിനേഷൻ ഇല്ല. നമ്മൾ സെക്കൻഡ് പൊസിഷനിലാണ് എപ്പോഴും
വരിക,
ന്യൂ എഴുതുന്നത്. ഓക്കെ. പക്ഷെ ഇത് മാറി വരുന്നുണ്ട്. ഇവിടെ ഫസ്റ്റ് പൊസിഷനിൽ പി വരുന്നുണ്ട്,
അതെ അതെ.
അതുപോലെ ഇവിടെ സെക്കൻഡ് പൊസിഷനിൽ ക്യൂ വരുന്നുണ്ട്.
അപ്പൊ രണ്ടാമത്തത് പോസിറ്റീവ് ആവും അല്ലേ?
അപ്പൊ നമുക്ക് അടുത്തത് നോക്കാം. ഓക്കെ, you take F2. All right, F2. See, F2. You say that you have got a q there, so you find small p. That's equal to dou F2 by dou q. Q first position ആണ്, കുഴപ്പമില്ല. Okay, so it's a plus here. All right. Similarly, you find ഇവിടെ capital P ആണുള്ളത്. Capital Q is equal to dou F2 by dou P. Okay. P is in the second position, so these positions are correct. Right. So here again it's plus. Okay.
Okay. ഒരു ഡൗട്ട് കൂടെ ചോദിക്കട്ടെ. അതില് നമ്മളിപ്പോ ആദ്യത്തെ രണ്ടെണ്ണത്തിൽ രണ്ടും പി ആണല്ലോ കണ്ടത്.
അതെ, അത് ഇവിടെ q ആണെങ്കിൽ, ഓക്കേ, ഇവിടെ q ആണെങ്കിൽ we can only find dou f1 by dou q.
Okay.
Then you get p.
Okay.
ഇവിടെ q ആണെങ്കിൽ you can find dou f1 by dou capital Q. That's capital P.
Okay.
Okay. Now we have to invert these equations sometimes. Okay. Equation as such transformation equations are we can invert these equations in order to find the transformation equations. Okay.
Mm.
Right. So yeah. So basically, if you invert this equation, you got a functional dependence Q, capital Q, T under, right? This equation invert you can find F1 as function of capital P and capital Q like that. Okay. So these sets of equations determine all the transformation equations. That's all we demand. That's all we say. This need not be the exact transformation equations. We can find the transformation equations from this by inverting this or rearranging these equations. All right. We assume that these equations are invertible. Is this fine?
Okay, okay.
Yeah, that's how we do it. These are the relations we have between the coordinates. Okay. Now this need not be exactly the transformation equations. See, these are not exactly the transformation. These are just relations. From this, we can find the transformation equations, all right, by inverting these equations. That's the basic idea. Okay. All right. Now let's look at F3. Okay. If you look at F3, we have got P inside. So we see that since we have P here, what we get is a relation for small q. That is dou F3 by dou P. Okay. You see that P has come in the first position here, right? Okay. So you have a minus sign. This is a way to remember that. So there is nothing really serious about it. But this is helpful in doing problems. Okay. So here I have got a capital Q. What you get by differentiating is the corresponding conjugate momentum, capital Q. That's dou F3 by dou Q. Okay. But this Q here is in the second position. Am I right? Yes?
Yes, yes.
So you have a minus sign. Okay. If Q comes in the second position, you give a minus sign. Okay. If P comes in the second position, it's plus. If P comes in the first position, you give a minus sign. That's the way to remember. Whether it's old Q or new Q doesn't matter. Okay. All right. So the old coordinates come only in the first position. It doesn't really matter. Now F4. Okay. You see that you have got a small p here. So the equation you have is small q is dou F4 by dou P. But we see that momentum has come in the first position here, right? So there's a minus sign. Okay. Similarly, here we have capital P. So correspondingly, you get capital Q. That's dou F4 by dou P. Is there a minus sign? Do you need a minus sign there?
No, second position.
P is in the second position. Okay. I don't know. Yeah, this works. Okay. It is helpful. Is this fine? So in a question, all right, they may give you a particular generation function like this. F is equal to QP. Okay. Now you don't need to know which type it is. Okay. You can write this as f of q comma capital P. What are the equations? You don't need even to know which thing is it. You don't need to remember the equations. Okay. You write just the old one in the first position and the new one in the second position. That's all. Okay. This is capital P. Okay. Now the transformation equations you need to find small p is equal to dou f by dou q. Okay, q is in the first position, no problem. And capital Q is equal to dou f by dou p. Okay, p is in the second position, no minus sign. Right. Now, incidentally, you may identify this as what is this? This is q with p. Q p. Right. It's f2. Am I right? It's f2. Okay, it's f2. But you don't even need to identify this. You just arrange it in such a way that in the first argument you have the first argument is the old coordinate or momentum, whatever it is, and the second argument is the new thing, whatever we have here. Okay, and then you can get the transformation equations using this technique to remember it. Okay. So you don't have to remember all these equations in order to solve problems. You just use this trick. You'll see it's very helpful when you get a problem in your examination. you'll see that remembering this rule will be very helpful. It saves you a lot of time. Okay. Also a lot of memory space. All right. Now, we'll just explicitly state some of the results so that we can solve problems more easily. Okay. The first thing is this. If the generating function does not depend on time, we can see this as an example problem. Okay, the generating function does not depend on time explicitly, then Hamiltonian will remain invariant, under a canonical transformation. Okay. Now, how do we prove this? We know that this old and new Hamiltonians are related by this relation. K is equal to H plus dou F by dou T, right? You can just check your previous notes. You'll see that the old and new Hamiltonians are related by this relation. Okay. Now, if F does not depend explicitly on time, then you see that F does not depend on time explicitly. Okay, if it doesn't have any explicit dependence on time, then you see that K is equal to H. Okay, so yeah, that's the result. That's easy. Now we write K equal to H, but you have to remember that this K, we have to write it as the new thing. We have to write it as function of capital Q, capital P, okay, and T. Okay, this is the function of generally, right? Q, this time may or may not be there. All right, even though it's exactly the same thing, the functional dependencies are different. All right, K you write always as function of the new coordinates and momenta, or the new phase space coordinates, and Hamiltonian, the old thing, you write it always as function of old coordinates. All right, small q, small p, and t. Okay. That's all. All right. And the next thing we need is this. We are going towards this thing. Okay. We can write it as a theorem if you like. This theorem for solving problems. Okay. So if the generating function, does not depend on time explicitly, how do I write it? Okay, explicitly, then the transformation is canonical. Okay, provided this combination, right? Pi dqi minus capital Pi dqi is a perfect differential. Is a perfect differential. Okay, this is important. Okay, so this theorem basically says that, okay, we can actually make strong statements like this, that this is necessary and sufficient for this transformation to be canonical, etc. But we'll just need this to solve problems. Okay, so this statement is actually saying, what it says is this: if you want to check whether a given transformation is canonical, so there's summation implied. Okay, so there is summation implied, summation over index I. We use Einstein summation convention. Okay, so if you need to check whether a given transformation is canonical, you just take this combination. Okay, and if it is a perfect differential, if you can write it in the form of d of something, okay, d of something, then you can say that this transformation is this particular transformation from small p small q to capital P capital Q or otherwise. Okay, this is a canonical transformation. Okay, now we prove this. So this is satisfied if the generating function does not depend on time explicitly. Okay. All right. Now, how do we check this? All right. Now, this is how we check it. All right. The condition for the defining condition for a transformation to be canonical, that we wrote like this: PIQI dot minus K plus dF by dt is equal to PIQI dot minus H. Okay, remember there is a summation implied here. Like, I'm not writing the summations. In the notes, I may give summation or not. All right, remember that this Einstein summation convention is always implied. So you have to sum over all these combinations. Okay, so here you see that this means that you can write dF by dt. Okay, so this is the condition for this transformation to be canonical. Okay, this is the starting thing. So dF by dt equal to PI QI dot minus PI QI dot, okay, minus, if you take this H to that side, you can write it as plus, because this becomes K minus H. Okay, this is true, right? Now, if this condition is satisfied, then this is canonical. Okay, this is the condition for transformation is canonical. If this condition is satisfied, transformation is canonical. Okay, this implies that if this condition is satisfied, the transformation is canonical. Okay, now what did we say? We proved in the previous thing that if the generating function does not depend on time explicitly, if, let's say, f, this generating function does not depend on time explicitly, okay, it has no explicit dependence on time, then K is equal to H, right? Am I right? Okay, so then you see that this implies dS by dt. Okay, if it does not depend explicitly on time, then we can simply say that PIQI dot minus PIQI dot. Okay, because K is equal to H if the function does not explicitly depend on time. Now you can multiply throughout by dt, because we have got QI dot is dQI by dt, capital QI dot is d capital QI by dt, right? So if you multiply by this thing, you see that dF is equal to PI, sorry, you can write it as dQI, PI dQI minus PI dQI. Right? Or in other words, we have got a dF here, right? This means that, or in other words, you just find PI dQI, summation implied. Now, if this is a perfect differential, okay, if is a perfect differential, it's a perfect differential, then the transformation is canonical. Okay, then the transformation is canonical. Is this clear?
Okay.
Did I write it correctly before? I have to check. Okay, I may have made in the theorem you have to write this. Okay, if this this is a perfect differential, then the transformation is canonical. Now we have two ways of identifying a canonical transformation. Okay, either you check for the fundamental Poisson bracket relations. If the new coordinates and momenta also satisfy the fundamental Poisson bracket relations, then it is a canonical transformation. Okay, sometimes it's easier to do this thing. You just take this combination and see if you can write it as D of something. If you can write it as D of something, then it is a canonical transformation. So if when you are given a problem, you can try these two methods and it works. Either of this method, I mean both methods work, but in some cases one method might be easier than the other. Okay, all right. Now, there are other ways of finding whether a transformation is canonical, but that involves the symplectic transformation, symplectic formulas, and we don't discuss that usually in this because it takes a lot of time. We don't need that also. Even solving that kind of problems takes a lot of time. So we'll just use these two methods, okay? And as we do problems, if some other method is more convenient, we'll discuss that.
Hello.
Yes.
ഈ Poisson bracket 0 ആണെങ്കിൽ canonical ആവൂലേ?
Poisson bracket 0, this Poisson bracket has to be 0. Qi with Qj, Pi with Pj has to be 0. Okay, but this has to be equal to Qi with Pj has to be equal to delta ij, which means that if you have single coordinate, Q with P has to be equal to 1.
ഇതൊക്കെ canonical transformation പറ്റുന്നതാണല്ലേ?
അതെ അതെ, ഈ കണ്ടീഷൻസ് സാറ്റിസ്ഫൈ ചെയ്യുകയാണെങ്കിൽ കാനോനിക്കൽ ട്രാൻസ്ഫോർമേഷൻ ആണ്.
അല്ലെങ്കിൽ പെർഫെക്റ്റ് ഡിഫറൻഷ്യൽ ആണല്ലേ?
അല്ലെങ്കിൽ പി ഡി ക്യു ഐ മൈനസ് പി ഐ ഡി ക്യു ഐ മൈനസ് ക്യാപിറ്റൽ പി ഐ ക്യാപിറ്റൽ ഡി ക്യു ഐ ഡി ക്യാപിറ്റൽ ക്യു ഐ ഹാസ് ടു ബി എ പെർഫെക്റ്റ് ഡിഫറൻഷ്യൽ. ഓക്കെ, ഇപ്പൊ ഈ രണ്ട് മെത്തേഡ് ഉപയോഗിച്ച് നമുക്കത് ചെക്ക് ചെയ്യാം. ഇപ്പൊ പെർഫെക്റ്റ് ഡിഫറൻഷ്യൽ ആണെന്ന് അറിയാൻ ചിലപ്പോൾ ഒന്ന് റീഅറേഞ്ച് ചെയ്യേണ്ടി വരും. ഇനി ഒന്നും ഇഫ് യു ഡോണ്ട് നോ ഹൗ ടു ഡു ഇറ്റ്, യു ജസ്റ്റ് ടേക്ക് the Poisson bracket. You know how to take the Poisson brackets. Okay, sometimes also when you do these kinds of problems, it's easier to use the definition of Poisson brackets. Okay, you can use the definition of Poisson brackets in this sense, all right, using the different derivatives. Most cases it is easier because you'll have square roots and some other functions like tan q or cot q inside the transformation equations. Okay, so it may be easier to use the definition. So whichever is convenient, you can use. Okay, they also ask such questions. They given two transformations involving constants alpha and beta and ask if the transformation is canonical, what is alpha and beta. Such questions are also asked. Okay, now there's another way. Sometimes you don't need to do. Sometimes they give the inverse transformation, all right, small q and capital P, sorry, small p and small q, and then it's sufficient to show that this is equal to 1 provided q with p is equal to 1. All right, so we assume that q with p equal to 1. If the inverse transformation is given, we assume that q with p equal to 1 and check, provided this assumption, does this hold? Then we can say that it is a canonical transformation. Okay, like that. Let's do a problem then. All right, we'll first see a few examples for canonical transformations. All right, simple examples, and then we'll go to problems. Or do you want a problem? Right, I think I'll give you a problem immediately. Okay, so all right, here is a question. Just do one example problem and then we'll see more examples of canonical transformations. Okay, important examples. Show that the following transformation is canonical. Okay, you've got capital Q is equal to square root of 2q e raised to alpha cos p, okay, and capital P is equal to square root of 2q e raised to minus alpha sin p. Okay, alpha is a constant. They say alpha is a constant, right? So what you need, so they are asking whether this is a canonical transformation or not. Okay, the question is whether this is a canonical transformation or not. Okay, all right. Now, how do we do this? All right. we could actually check all the fundamental Poisson brackets. Okay, be on the safer side and check all the Poisson brackets. So let's say Q with Q. Okay, Q with Q. Now this is 0 by definition, right? We know that this is 0 by definition. So we need not check this. This is true. Okay, what we need to check is whether Q with P is equal to 1. Okay, whether Q with P is equal to 1. Okay, all right. Now this is just one dimension. So this is easily done. Which is the easiest way to do it? Maybe we can first combine the terms and then use the derivative technique. Right? So if you take Q with P, you see that the square root of 2Q has a non-zero commutator with only sine P. Okay. Similarly, this cos P has a non-zero commutator with square root of 2Q. Alpha is a constant, we can pull it outside. Okay. So we'll just simplify immediately. This you can write it as, we need to check this. Okay. So this you can write as, the first non-zero Poisson bracket is, I hope you already know how to do this, or you just do all the steps. Okay. Square root of 2Q, okay, with sine P. Okay, and you have got e raised to alpha, e raised to minus alpha here, they multiply to 1. Okay, and you have got a square root of 2Q here, right? This cos P, square root of 2Q, you have to pull out. So this is square root of 2Q cos P. Am I right? You have just combined this. I've just used one of the identities using Poisson brackets, so that reduces the number of steps. There's also one more non-zero Poisson bracket, that's cos P with square root of 2Q. Okay, so that I write it as cos P with square root of 2Q. Okay, cos P with square root of 2Q. And what do we have? E raised to alpha, e raised to minus alpha is 1. You've got a square root of 2Q here and a sine P there, right? Okay.
Okay.
All right. Now this is now it's better to use the fundamental definition, because you have got a square root of 2Q, or you have to square this and then use some other identity. It's better to use the fundamental Poisson bracket definition. Okay. So if you see here, it's the derivative of the first one with respect to P multiplied by the derivative of the second one with respect to P, right? And then in the opposite order. So if you do that, you see that this is equal to, you take the derivative of this with respect to Q. So that is, so you take the derivative of the first one with respect to Q. Okay. What do you get? This is 1 by 2 square root of 2Q. Okay. Derivative of this with respect to Q. And then you have got a 2 there. Okay. All right. Okay. And then you have got derivative of the second thing with respect to P. Okay, that becomes cos P, and you have got a square root of 2Q there and cos P. Okay, the second term is automatically 0. You don't have to write it, because the derivative of the first one with respect to P, okay, and the derivative of the second one with respect to Q, these are 0, so you need not write it down. Am I right? Okay, so you just write the second thing. Right? I'm just simplifying it. You see that here you need to take the derivative of the first thing, the first term in the Poisson bracket fundamental relation is 0, right? Because dou cos P by dou Q is 0. Okay, so you only take the second thing, that's enough. Right? So for the second thing, you have a minus sign. So it becomes, I'll just write it, minus dou cos P by dou P, that is minus sine P. Okay, that's minus sine P, and then square root of 2Q, again it is multiplied by 2 divided by 2 square root of 2Q. Okay, just so you got 2 minus, it becomes plus. Okay, all right. Now what do you get here? This is 1 by square root of 2Q.
ഒരു സൈൻ പിയും കൂടി ഇല്ല അവിടെ.
എവിടെ? I'm sorry. Sine P. Yes. So now you see how it's working, right? This goes, and this there's a square root of 2Q also, right? Am I right?
Yes.
They all go. So it's cos square p plus sin square p, which is equal to 1. Okay? So this is a canonical transformation. This is the way to check whether it's a canonical transformation. Okay. You could also check q with q just to be sure. All right. But we already know that any two functions, u with v, u with u is 0 and v with v is 0. So that you can either check, or you can sometimes you can use it as an equation, right? Because if you need to determine some of the constants or some of the unknowns, you may need a number of equations. Right? So in that case, you can use it as an equation that q with q is 0 and p with p is 0. Right? Using those relations, you may get what do you say, an equation connecting these constants, and then you can use it to solve for the constants. All right? These are different ways of doing it. Now, such problems are asked to check whether a thing is canonical. They say they give options to check whether which of the following transformations are canonical. Such kind of questions are asked. Okay. Now let's look at some simple but important examples. Okay. Can you see the board clearly?
Yes.
All right. Let's check this. F is equal to example 1. Okay, some examples of canonical transformations. F is equal to, let's say, QIPI. Okay. Now, which type is this? Which type of generating function is this? Does this belong to any type that we are familiar with? This is F2. Am I right?
F2.
F2. But it doesn't matter. This is actually F2. It doesn't matter. You know the transformation equations, right? Because we have got QI there. We can say PI is equal to dou F by dou Qi. Okay, actually I have to take dou F by dou Qj and use the Dirac, I'm sorry, the Kronecker delta. So it's that basically comes back to this. Pi is equal to dou F by dou Qi. That's equal to, let's write J here just to be clear. Okay. The summation over J is implied. Okay, there's actually summation over J, repeated index. Okay. Now dou F by dou Qi, this means this is equal to delta, because if you take dou Qj by dou Qi, you get delta Ij Pj. Again, this is equal to P. This is capital. This is capital. Okay. P I. Okay. So you see that small pi is equal to capital Pi. All right. Now, what about the other transformation equation? The other equation, you know that, yeah. This is capital P. So capital Q is equal to, or Qi, I'll just write it down this time. Qi is equal to dou F2 by, just write it, okay, Q comma capital P. So there is no minus sign, dou F2 by dou Pi, and that's simply Qi. Okay, you just follow the steps. So this is actually an identity transformation, right? This generating function gives you the identity transformation. This can be asked, okay, which among the following statements is true about this transformation, that is an identity transformation like that. Okay? This is an identity transformation. What does it do? What it does is that it makes a transformation, but the new coordinates are the old coordinates and the new momenta are the old momenta. Okay. This is known as an identity transformation. All right. So this generating function generates an identity transformation. Generates an identity transformation. Generates an identity transformation. Okay. Let's look at an example for type 3. Let's say f is given by Pi Qi. Okay, you see that this is a function of Pi Qi. You write the old one first and the new one second. Okay, so this is actually F3, but even without knowing it's F3, you know how to write the transformation equations, right? Because we know that we have got this equation Qi is equal to dou F3 by dou Pi with a minus sign. Am I right? Okay, so this is equal to minus Qi. Okay, just do it and you'll see that there's a summation implied. Okay, there's a summation implied, sum over j. Okay, so like that. So it's minus Qi. Similarly, you see the corresponding equation here. This is Qj. So what you get is capital Pi. That's equal to dou F3 by dou Qi. Okay. Here Qi is in the second position. Again, you will get a minus sign. So it's equal to minus Pi. All right, minus Pi. Fine. Now, what does this mean? Okay. So you see that you get the transformation equations by inverting this. This is trivial inversion. You see that you get the new coordinates in terms of the old coordinates and momenta. You get the here again. You get the new momenta in terms of the old coordinates and momenta. This is a special case where we just take what do you say, old coordinates and momenta and give them a minus sign, multiply it with a minus, and that is a canonical transformation. Okay, so this is an identity transformation with a minus sign. Okay, F3 is equal to PJQJ. This generates an identity transformation with a minus sign. Okay, with a minus sign. Okay, all right. Now, more generally, you can think of a generating function f2 of this form. Okay, it's fi. There's a summation implied. Q1, Q2 up to Qn, and in principle, there may also be a time there. So multiplied by Pi. Okay. Now, what does this mean? This means that one part of it completely depends only on Q1, Q2 up to Qn. Okay, and the other parts are the new momenta. These are the new momenta, right? So if you do this thing, this is of the form. This is of the form F2 of, what do you say? It's Q with P. Am I right? It's Q with P. Okay. So you see that this means that we got small q here. So Pi is equal to dou F2 by dou Qi. Okay. And capital Qi is equal to dou F2 by dou Pi. Okay. What do you get here? I've got a Pi there. Okay. There's I said there's summation over I. We could use J there. So just to be clear. All right. So if you take, you'll get a delta Ij, and when you sum over, you simply get Fi of Q1, Q2 up to Qn and T. All right. So here you see that the new coordinates, all right, the new coordinates are purely functions of the old coordinates. Right. The new coordinates are simply a rearrangement or another combination of the old coordinates alone. There are no momenta involved. Okay. So there is no momentum dependence here. Okay. Now this kind of transformation we discussed earlier. It's an example of what's known as a point transformation. Okay, a point transformation in configuration space. All right. This is an example of point transformation. Point transformations are transformation of this form. Qi is equal to Qi of old coordinates and time. No momentum dependence. Okay. Now if this is invertible and it's all independent on all this, now yeah, it has to be, if it's a point transformation, it has to be invertible and all these things have to be independent of each other and all that. Okay, so the result what we have here, all point transformations are canonical. Okay, the result, because we are talking about canonical transformation, the result I want you to remember, I want you to take home is that all point transformations are canonical. Okay, so if you need to identify a transformation and what you are given is a point transformation, then you know that it's a canonical transformation. Okay, all right. All right. So all point transformations, in the sense that if the new coordinates are the functions of the old coordinates alone, okay, then we have written down the result. All point transformations are actually canonical. Okay, there are more details about that, but we don't do that. Now there's another enlightening or more thing, that a transformation that gives you more idea about how abstract this can be. Okay, let's look at the canonical transformation by a generating function f1. Okay, let's just write it as qk qk. Okay, there's a summation implied. What are the corresponding transformation equations? Pi is equal to dou f1 by dou qi. Am I right? Yeah. So that's equal to, if you take dou f by dou k, you get capital Qi. What you see is that the new coordinates, all right, the new coordinates are the old momenta. Am I right? The new coordinates are the old momenta. Okay. Similarly, you get capital Pi. It is dou f1 by dou qi. Okay, is there a minus sign? Is there a minus sign? Do we need a minus sign there?
No.
But there is a minus sign, right? Because Q is in the second position. Right?
So ആദ്യത്തേത് okay, transformed coordinate ആണല്ലേ.
So this gives you actually a relation between old and new coordinates. Okay, you can invert it to get the transformation equations. Here you get directly the transformation equations. Okay, the new coordinates are equal to the old momentum. Okay, fine.
Okay.
What do we get here? That's equal to Pi equal to minus Qi. Okay, so you see that the new coordinates are the old momenta. New coordinates are the old momenta, and the new momenta are minus the old coordinates. Right, the new momenta are minus the old coordinates. So what you have here is, so from these relations you find the transformation equations. It's very trivial. Qi is equal to Pi and Pi minus Qi. Okay, now you see what we have done here. What we have done is that we have taken the old momenta and considered it as the new coordinates, all right, in a different system, and we have taken the old coordinates here and given it a minus sign to make it new momenta. All right, you remember that this minus sign has to be there because there's a slight asymmetry between position and momentum. Because even in new coordinate system, dou k by dou pi should give you qi dot, and such relations have to be satisfied. So this minus sign has to be there, right? It cannot exactly be the same. You cannot simply invert the position and momenta. When you invert the position and momenta, you get a minus sign somewhere, right? But the thing is that what this means is that now the position and momenta, there's no real distinction. Okay, so when you hear momenta, you think something like mass multiplied by what? When you hear momentum, you think that it's something like mass multiplied by velocity or some different combination of it. Okay, and when you think of coordinates, you think some sort of positions. Okay, but here we have taken, even if you start with such a thing, we can go into a system where these are the new coordinates and these are the new momentum. Okay, so it's more abstract and there's no real division between coordinates and momenta. We can just call them as coordinates. Okay, so it's good to lose this connection between the real world, from the real world, Okay. So you see that even if it is mv, this may have the dimensions mv, but still this may have the dimensions mv, but still we can consider them as coordinates. Okay, this is important. So it's making it more abstract. We started with the Lagrangian, where we only had the coordinates and we talked about the configuration space. We came to Hamiltonian mechanism, we had coordinates and momenta, but again we had some sense of what we mean by momenta. For example, for a particle in space, it's mx dot. The momenta in one dimension, it is mx dot, etc. All right. Now, when we come to canonical transformation, we see that what you choose as momentum and what you choose as coordinate is completely arbitrary. It doesn't matter as long as the equations are satisfied. Okay. So even if you start with some sort of momentum of the form of mx dot, you can take a coordinate system, or you can take a different kind of phase space where these are the new coordinates and the other thing are the new momentum. All right. So what we have is basically, yeah, it is made more abstract and it's easier to deal with. Okay. So we can say this transformation interchanges the momenta and the coordinates. Okay. Right. You can also check that this generating function f4 is equal to pi capital EI. Okay. Summation implied. This also generates the same transformation. You can show that this also generates the same transformation. Okay. Now, this example actually is important. It shows the independent status of coordinates and momenta. Okay. So distinction between coordinates and momenta is now almost gone. It's just a name. Right? You take what you have is a phase space, and some of them you call coordinates and some of them you call momenta. Right? What you have is a phase space, and n of the coordinates of phase space you call as position, and n of the coordinates of the phase space you call as the momentum. Okay. It doesn't need to have any connection at all with what you call as the momentum in your Newtonian or even in Lagrangian or Hamiltonian formalism. Okay. You just need to be careful. Okay. You cannot have Qi equal to Pi and Pi equal to Qi. This is not possible. All right. This is not possible. Somewhere there has to be a minus sign. Okay. Only then the equations of motion will come out right. Only then it will be a canonical transformation. Okay. All right. Okay. Now we can also think about a combination of the generating functions as a new generating function. Okay. So we can have a transformation that leaves some of the QP pairs unchanged. Let's also talk about a transformation where some of the QP pairs are unchanged. Okay, which means that to a part of the phase space coordinates, you give an identity transformation. Okay. Unchanged and interchange the rest. Interchange the rest. Okay. All right. Which means that we'll have, for example, for 2 degrees of freedom, this transformation would mean we'll take Q1 is equal to Q1. Okay. And Q2 is equal to, sorry, and P1 is equal to small p1. All right. Some of them are unchanged. Okay? And other one we interchange. Okay. Q2 is equal to P2 and P2 is equal to Q2. Is this possible? Is this possible? Can we do this? No, this wouldn't be a canonical transformation. As I said, when you interchange, you get an extra minus sign because of the asymmetry in the equations of motion. Okay, we know that P dot is minus dou s by dou. So this is the transformation for this transformation means this for 2-dimensional system. Okay, 2 of the coordinates, old coordinates and momenta, we map it to new coordinates and momenta. Q1 equal to, and the rest you interchange. Okay, now this can be achieved by a generating function. F is equal to Q1 P1 plus Q2 Q2. Okay. All right. So such questions can be asked. Okay, what's the generating function corresponding to this? We have already seen that this is the identity transformation, and this just interchanges the positions and momenta, right? Yeah, I think that's what we, just a second, let me check. Yeah, Q2, Q2, right? This was F3. So this is actually a combination of QP. This is F2. This is a combination of F2 and this is F3, I think. Right, that's F3, I think. Oh. No, no, no. This is not F3, right? This is F1. It's F1, I think. So what we have here is a combination of F2 and F1. Is it F1? I think it's F1, right? Yeah, it's a combination of F1 and F2 types of transformation. So you can also have such generating functions. It doesn't matter. So what we have is like a basis set of generating functions. All right, F1, F2, F3, F4. We can also have combinations of these generating functions, which also give you canonical transformations. Okay. All right. Next class we'll do problems to check whether certain transformations are canonical using both these methods. Okay, and such problems are being asked. And from all these things, you may get some question, all right? Conceptual question might be asked. So it's good to be familiar with this. At least when you see a question, you know what you're looking at. Okay. All right. Then we'll have the next class on Monday. Okay, we'll continue on Monday. Thank you.
Thank you.
Okay.